morning, Mananda. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about one of the important topic in transmission lines as a Smith chart configuration. So, it takes lengthy analysis. So, in this particular lecture, we'll be discussing about how we are going to configure this Smith chart. So, basically, a Smith chart is a graphical tool in order to represent reflection coefficient and normalized impedances, as well as standing wave ratios. So, to calculate reflection coefficient and standing wave ratios, we use two different methods. One is theoretical analysis with the help of all the fundamental properties or characteristics of the transmission lines, and with the help of graphical method, the help of Smith chart, right? So firstly, what do you mean by Smith chart? How it is going to configure? Now, in order to configure this Smith chart, what are the required mathematical equations we are going to learn in this particular lecture. So firstly, Smith chart. So Smith chart named after his its inventor Philip Smith, as the who invented the Smith chart. Depending upon his name, has given the chart a graphical representation of a chart called a Smith chart, developed in 1940s and is essentially a polar plot of the complex reflection coefficient for arbitrary impedance. Arbitrary means our own defining impedance. It is our choice to define, or it is our choice to select that particular impedance. Right? So basically it is a polar plot of the complex reflection coefficient plane. So basically the Z means it is the notation for the impedance, which consisting of real term as resistant and the reactance term or imaginary term as X, right? Depending upon like this, the complex variable called impedance, reflection coefficient gamma is also a consisting of polar form or complex form, which is expressed in terms of gamma equal to U plus JB, right? So in order to consider all these complex variables like for impedance as R plus Jx and for reflection coefficient gamma equal to U plus JB, now this is the fundamental analysis. So Smith chart can be used to display several parameters including impedances, admittances, reflection coefficients, and scattering parameters of antennas. So impedances all are representing with Z, and admittances means Z is equal to R plus Jx here, and admittances case Y equal to G plus JB, where a real part is given as conductance and the imaginary part is given as susceptance, including for this admittance. And reflection coefficient gamma equal to U plus JB. All these are comes under complex forms, which are combinations of real parts as well as imaginary parts. So Smith charts can be used to display several parameters including impedances, admittances, reflection coefficients, standing wave ratios, and scattering parameters. It is a graphical figure obtained by superposition the constant resistance and constant reactance circles within that unit circle in the complex reflection coefficient plane. So generally, what do you mean by Smith chart means it is a graphical figure obtained by superposition the constant resistance circles along with the constant reactance circles within the unit circle in complex reflection coefficient plane. So basically this reflection coefficient is a complex form or plot or polar plot which has magnitude and the phase functions. Magnitudes are always real terms and phase functions always represent imaginary functions. Now, Smith chart is plotted on the complex reflection coefficient plane in 2 dimensions and is scaled in normalized impedance and normalized admittance. Normalized impedance is denoted with Z bar and the normalized admittance is represented with Y bar or both. So with the help of this Smith chart, we can frame normalized impedance or normalized admittances or sometimes both. using different colors to distinguish between them. So for resistance circles, we use one color. For reactance circles, we use another, such that different colors are used to distinguish or different, to identify those, whether it is impedance chart or else admittance chart or both. Then Smith charts can be categorized into three different types. Basically, different types of Smith charts are there depending upon the term which we are going to represent on the Smith chart. See, if you are going to design impedance, then it is said to be the impedance Smith chart, or simply these are called Z stats charts, where Z is the notation for impedance. Okay, so the impedance Smith charts are also called as Z charts, and the admittance Smith chart is also called as Y charts. Along with that, the impedance Smith chart means it consisting of both impedance. Impedance means it consists of both impedance and admittance. Right? So impedance means it is a combination of impedance plus admittance, and the charts are called collectively YZ charts. So there are basically three different kinds of Smith charts are available: impedance charts and admittance charts, along with that impedance charts. Impedance charts are simply called as Z charts, and admittance charts are called as Y charts, along with the impedance charts are YZ charts. So generally we used to, means most popular Smith chart is based upon impedance only. Hence impedance Smith charts are most popular nowadays. Right? Depending upon means, now to represent the reflection coefficient plane on normalized impedance and normalized admittances, there are different kinds of impedance Smith charts are available: impedance charts, admittance charts, and impedance charts. Right? So most probably we are going to use here impedance charts. That's why impedance Smith chart. So the impedance Smith charts are usually referred to as the normal Smith charts, since they relate with the impedances. Okay. See, normally the impedance chart or impedance Smith chart is looks like this. See, these are all the circles which are representing, means these circles are representing the constant resistance circles, and circles where this arcs are left side, and arcs are representing constant reactance circles. Constant reactance circles. Right? In order to draw this Smith chart, we need two different types of circles. One is constant resistance circles, and another one is constant reactance circles. Right? So to plot that Smith chart, we need means in order to represent, we use complex impedance plane as well as the complex reflection coefficient plane. Right? So to draw this Smith chart, first in order to configure this Smith chart, we are going to use polar plot which consisting of resistance circles as well as the reactance circles. Right? So firstly we are going to derive the mathematical equations for how we are going to draw the constant resistance circles and the constant reactance circles. From this we'll be drawing the Smith chart. So first, configuration of this Smith chart. How we are going to configure this Smith chart? Then based upon that, the finalized form of Smith chart is to be considered for the impedance as well as reflection coefficient calculations. So the Smith chart displays the complex reflection coefficient in polar form for a particular load impedance. Generally, this load impedance is denoted with ZL, and the characteristic impedance as Z0. Why? Because we are talking about reflection coefficient. So reflection coefficient of a transmission line, which is to be already derived in the previous lectures, that is given by ZL minus Z0 by ZL plus Z0, where ZL be the load impedance and Z0 be the characteristic impedance. Right? The Smith chart displays the complex reflection coefficient in polar form for a particular load impedance. And impedance is the sum of resistance and the reactance and is a complex number. Generally, we are representing this impedance is with Z and the resistance as with R and the reactance is with X. Right? So, impedance is a sum of a combination of resistance and reactance, and basically it is expressed in a complex number. So, the impedance at a location on a transmission line can be given by here Z is equal to R plus Jx, where R is said to be resistive part of the impedance and X be the reactance part of the impedance. Resistive part of the impedance as real term, reactance part of the impedance as imaginary term. And in general, the impedance at a location on a particular transmission line Z can be given by Z is equal to R plus Jx. Right? And from this, we are going to calculate normalized impedance. So to calculate this normalized impedance, see the normalized impedance at a location on transmission line, and it is given by, means, see, now consider this as the equation Z is equal to R plus Jx, and both sides if you divide with the Z naught. That Z naught is a notation for what? Characteristic impedance. Divide Z naught with both on both sides. Divide Z naught on divide with Z naught on both sides. Right? So now Z by Z naught equal to R by Z naught plus J into X by Z naught. Okay. This Z by Z naught is resembles with Z bar, and R by Z naught is given with real part of that, and X beta means Z bar equal to small r plus J X. Right? Where Z bar is equal to Z by Z naught and R equal to small r equal to R by Z naught, and small x is equal to X by Z naught. Okay. So to consider normalized impedance equation, that is Z bar equal to R plus Jx, we are dividing the previous equation, impedance equation at a particular line is Z is equal to R plus X Jx, and divide the total equation with the Z naught on both sides. Then Z by Z naught equal to R by Z naught plus J into X by Z naught. Now from that we will be replacing all the terms with the normalized impedance notation as Z bar equal to small r plus J into small x. Okay, where r is the reactance or resistance part of the normalized impedance, and small x be the reactance part of the normalized impedance. Okay, see here Z bar equal to R plus Jx, where Z bar is the normalized impedance, and the small r equal to R by Z naught, and x is equal to X by Z naught, and where Z bar is given by Z by Z naught. Right? So Z bar is the normalized impedance, and Z be the impedance on a transmission line, and Z naught be the characteristic impedance. Okay. Now the reflection coefficient at the location. See, previously we have considered first impedance on a location at the transmission line. Then from that we have been calculated this normalized impedance. Now first consider here the reflection coefficient at the location on transmission line, and it is given by gamma. Notation for reflection coefficient is gamma, and it is given by ZL minus Z naught by ZL plus Z naught, where ZL be the load impedance of a transmission line and Z naught be the characteristic impedance of the transmission line. Right? So consider this as the formula for reflection coefficient at the location on transmission line, that is gamma equal to ZL minus Z naught by ZL plus Z naught, and from that, see, consider that equation gamma equal to ZL minus Z naught by ZL plus Z naught. Now, if you take or divide the total equation with ZL numerator as well as denominator with Z naught, means ZL by Z naught minus Z naught by Z naught by ZL by Z naught plus Z naught by Z naught. So 2 gets cancelled, then this becomes ZL by Z naught is considered to be as Z bar. Okay, Z bar minus 1 by Z bar plus 1. So reflection coefficient on a line gamma can be written as in terms of normalized impedances Z bar minus 1 by Z bar plus 1. See, these two gets cancelled, then ZL by Z naught is considered to be as normalized impedance, and that is given by Z bar minus 1 by z bar plus 1. As normalized impedance is complex, as normalized impedance is complex form, then gamma will also be complex. As we know that z bar is given as here r plus jx means it is a complex form. Hence, if it is complex form, gamma will also be complex. Why? Because gamma includes the normalized impedance, right? So, if z bar is a complex form means z bar, formula for complex normalized impedance is given as r plus jx. If you substitute this z bar by r plus jx in this equation, it also includes the real and imaginary terms. Means if the equation consisting of real and imaginary terms, it must be a complex number. Hence, as normalized impedance is complex, gamma, reflection coefficient of a transmission line gamma, will also be complex, right? So from that it is given by gamma equal to u plus jv, and that can be. So where u is the real part of the reflection coefficient plane and v be the imaginary part of the reflection coefficient, right? And modulus of gamma is given by here magnitude of the reflection coefficient and e power j theta be the phase function for that. Okay, so from the reflection coefficient plane, we have considered the formula as ZL minus Z0 by ZL plus Z0. Now from that, we have been written one relation, that is reflection coefficient in terms of normalized impedance as Z bar minus 1 by Z bar plus 1. Okay, now from that relation, we have got what are that? Gamma equal to u plus jv and z bar equal to r plus jx. U plus jv, see here, gamma equal to u plus jv means if you substitute gamma equal to z bar minus 1 by z bar plus 1, which is equal to z bar means what? R plus jx minus 1 by r plus jx plus 1. So, r minus 1 plus jx by r plus 1 plus jx. So, if you consider like that, or z bar in terms of gamma means we know that this z bar is equal to gamma equal to z bar minus 1 by z bar plus 1. Now, from that, gamma can be written as u plus jv. And if you want to write that one, now, gamma equal to u plus jv and z bar equal to r plus jx from the previous one. So, here z bar is known as normalized impedance and gamma be the reflection coefficient plane. So, both can be representing as complex numbers, and it is given by gamma equal to u plus jv and z bar equal to r plus jx. In case of passive loads case, resistance R is positive and it lies between 0 and infinity. We are assuming in case of passive loads, if R is positive, then the R values are lying from 0 to infinity. Means only positive axis only. Means first quadrant of or 1/4 quadrant of this will be considered as the impedance plane, right? And 0 and infinity, and x can be positive or negative, lies between minus infinity to plus infinite, right? So resistance part is lies on the first quadrant of x impedance plane, and reactance part is either positive or negative depending upon the consideration, and where x values are ranging from minus infinity to plus infinity. And any passive load can be represented by a point in the right half of complex reflection plane, complex impedance one. So see here, if you observe, the first one is called impedance plane and the next one is complex reflection coefficient plane. See, if you observe here, in the horizontally we are taking its value as r and vertically imaginary part as x. This is the impedance plane and r plus jx is the notation. So real terms are considered to be on x and imaginary terms are considered to be on y. So this is a simple impedance plane, and where x value or resistance R value is ranging from 0 to infinity. And if you consider x is the imaginary one, and where x values are ranging from minus infinity to plus infinite, right? So here if you observe, this is the complex reflection coefficient plane, and our real term is to be considered on the x-axis and imaginary part is considered to be on y-axis. So this is u and here it will be jv, right? So this is the impedance plane and here it is complex reflection coefficient plane. As we know that gamma equal to u plus jv, which is equal to modulus of gamma into e power j theta, right? So where this theta can be considered as like this between real and imaginary terms. Okay. So in case of passive loads, if R is to be assumed as positive, hence R values are ranging from 0 to infinity. And if you consider reactance, whether it is positive or negative, and it lies between minus infinity to less than finite. Depending upon that, we have seen the impedance plane and the complex reflection coefficient plane. Then, the magnitude of reflection coefficient gamma is always less than or equal to unity. So this and all already we have analyzed in the previous lectures, that is under reflection coefficient and the standing wave ratios of a transmission line is we have performed one lecture on this. Then there we have analyzed the magnitude of the reflection coefficient modulus of gamma is always less than or equal to the unity. Means gamma is ranging from 0 to 1 only, right? And any reflection coefficient can be represented by a point in a complex reflection coefficient plane within a circle of radius as unity, and that can be considered as modulus of gamma is less than or equal to 1. As we know that gamma in terms of normalized impedances, gamma equal to z bar minus 1 by z bar plus 1. Okay. Then for every point in complex impedance, there exists a corresponding point in complex reflection coefficient plane. Why? Because it includes both normalized impedance as well as the reflection coefficient plane of a transmission line. Now, see, in order to find the resistance and reactance circles, first consider reflection coefficient gamma in terms of normalized impedance. That is gamma equal to z bar minus 1 by z bar plus 1. And if you multiply these two, gamma into z bar plus 1, cross multiplication between 2, then gamma into z bar plus 1 equal to z bar minus 1. Right? Now from that, z bar equal to 1 plus gamma by means gamma equal to z bar minus 1 by z bar plus 1. Now from this z bar can be expressed in terms of gammas. Means in order to express the normalized impedances in terms of reflection coefficient, then gamma into z bar plus 1 equal to z bar minus 1. Now gamma z bar plus gamma equal to z bar minus 1. Now if you take this z bar or minus 1 into this side, 1 plus gamma equal to z bar minus gamma into z bar. Now if you take here z bar as common, 1 minus gamma as here 1 plus gamma. Now from this z bar is equal to 1 plus gamma by 1 minus gamma. Okay. So reflection normalized impedance z bar can be expressed in terms of reflection coefficient means 1 plus gamma by 1 minus gamma. Okay. So this is the way we have got z bar equal to 1 plus gamma by 1 minus gamma. Now from this, already we know that gamma equal to u plus jv and z bar equal to r plus jx. Okay. So normalized impedance in terms of resistance and reactance as r plus jx, and reflection coefficient in terms of real and imaginary as u plus jv. Right? And we know that, see here, gamma equal to z bar minus 1 by z bar plus 1. Okay. Now z bar means what we have considered here. Z bar is equal to first r plus jx is equal to z bar equal to 1 plus gamma by 1 minus gamma. Okay. Now consider this is the relation. In that we just substitute all the complex forms as r plus jx equal to, and 1 plus gamma means u plus jv by 1 minus u plus jv. Okay, which is equal to 1 plus u is the real term plus jv by 1 minus u is the real term and minus jv is an imaginary term. Now to separate the real and imaginary, we need to rationalize this one with 1 minus u plus jv by 1 minus u plus jv. Right? So if these two gets cancelled, the equation remains the previous one only. It won't alter. So which is equal to, so 1 plus u plus jv into 1 minus u plus jv. Okay? And which is equal to 1 plus u plus jv into 1 minus u plus jv. Okay. Then by in the denominator. If you observe, this looks like A and its value is also A, and this is B and this is related to B. See, if you observe, A value is 1 minus U and B beta JV, right? So it looks like A minus B into A plus B form. So as we know that A minus B into A plus B equal to, according to the exponents, its value is given by A square minus B square, right? So in the denominator, a square means 1 minus u whole square. Then minus, already in the formula itself negative is there. We need to multiply with the j and j. Then j square value becomes minus 1. Then minus of minus becomes plus into b square. Okay. Now cross means multiplication of numerator term becomes, see, 1 plus u into 1 minus u as the first term. And from this 1 plus u into jv as the second, and 1 minus u into jv as the third, and jv into jv means j square into v square by, in the denominator, 1 minus u whole square minus j square into v square becomes plus v square. See here, gamma equal to u plus jv and z bar equal to r plus jx. Now from that, z bar equal to r plus jx is equal to, this is the way we have considered. Now multiplication between 2 means 1 plus u into 1 minus u. This is also looks like a square minus b square form. Then it becomes, see, a square 1 minus u square means minus u square, and here j square into v square value becomes minus, j square value is minus, then minus v square plus multiplication between these two, jv plus jvu plus jv minus jvu, right? So this j square into v square value is minus v square, it becomes, means j square value is minus 1, it substitute negative, then 1 minus u square minus v square plus jv into jvu between these two, jv minus jvu as like this. So plus jvu minus jvu gets cancelled, and from this if you separate the real and imaginary, then 1 minus u square minus v square plus jv and jv are left out. If you are going to add those two, plus 2jv by, in the denominator, 1 minus u whole square plus v square is left out. Okay, 1 minus u square minus v square plus 2jv by 1 minus u whole square plus v square. Okay, so from this we can separate real and imaginary terms. So to, in order to separate real and imaginary terms, see here, if you observe in the numerator, only real term is 1 minus u square minus v square. So 1 minus u square minus v square by 1 minus u whole square plus v square as the real term, and 2jv by 1 minus u whole square plus v square as imaginary. Okay, now from this, r is equal to, see, in the left hand side also we have real and imaginary terms as r and x. So now equate real part and imaginary part separately. Then real part r is to be given by r equal to 1 minus u square minus v square by 1 minus u whole square plus v square, and imaginary as 2v by 1 minus u whole square plus v square, right? So this is the real term, and here it will be an imaginary term. So depending upon this one, resistance and reactance of normalized impedances, we'll be calculating constant resistance circles and constant reactance circles. If you merge those two, then resultant graph looks like, our chart is said to be Smith chart. right? So Smith chart is a graphical representation of complex reflection coefficient plane, and it consisting of resistance circles and reactance circles. Okay, so depending upon this resistance and reactance circles, how we are going to draw the circles and all. See, first consider, in order to find the constant resistance circles, in order to find constant resistance circles, first consider real term, right? So to find constant resistance circles, first consider real term in the previous equation, that is R equal to 1 minus u square minus v square by 1 minus u whole square plus v square. Okay, so from this, see, consider the real term as R is equal to 1 minus u square minus v square by 1 minus u whole square plus v square. Now cross multiplication between these two, then it becomes R into 1 minus u square plus v square, which is equal to 1 minus u square minus v square. Now from this, cross multiplication between 2 gives us R into 1 minus u whole square plus v square equal to 1 minus u square minus v square, right? So now 1 minus u whole square means, if you expand this one in terms of a minus b whole square formula, a minus b whole square equal to a square plus b square minus 2ab, right? So in place of a, here we have 1 minus u whole square. 1 minus u means plus b square is u square minus 2u. Okay, 1 minus u whole square, right? So, and plus v square into r means 1 minus u whole square plus v square into total plus v square into r gives us, means r plus r into u square minus 2r into u plus r into v square. See, if you expand all of a minus b whole square formula plus v square by adding, and if you multiply the total inside the term as 1 minus u whole square plus v square with r, then resultant will be given by here r plus r into u square minus 2ru plus r into v square, right? Which is equal to, on the RHS part, 1 minus u square minus v square is to be left out. Now, separate here, see, all or else they take the 1 minus u square minus v square, the total term, into LHS, then it becomes r plus ru square minus 2r into u plus r into v square, then 1 becomes minus 1, minus u square becomes plus u square, and minus v square becomes plus v square, which is equal to 0, right? Now from this we can separate r terms, u square terms and v square terms, right? Now from this r and this 1, first terms 1 and 1 means r minus 1, right? And if you take u square as common, this and this between these 2 and 2, now between 2 and 2, if you take u square as common, r plus 1, right? Plus, and between v square means, in order to consider v square as common, see r v square and v square. This is 3 and 3 are to be considered. So between 3 and 3, if you take v square as common, r plus 1. Then minus, which is left out, only this term is left out, that is minus 2r into u. Okay, so r minus 1 plus u square into r plus 1 plus v square into r plus 1 minus 2r into u equal to 0. Okay, now to write the circle equation, we just consider here, see, if you take r plus 1 as common between all the terms, if you take r plus 1 as common between all the terms, right? So r minus 1 by r plus 1, right? See, or else if you take first r minus 1 plus u square into r plus 1 plus v square into r plus 1 minus 2r into u equal to 0. Now consider this equation, and if you take r plus 1 as common between all, means r minus 1 by r plus 1 plus u square into r plus 1 by r plus 1 plus v square into r plus 1 by r plus 1 minus 2r or u by r plus 1 equal to 0, right? So here r minus 1 by r plus 1 as one ratio, r minus 1 by r plus 1 plus these two gets cancelled, u square plus v square minus 2 into 1 by r plus 1 into u equal to 0. See, r minus 1 by r plus 1 plus u square plus v square minus 2 into 1 by r plus 1 into u equal to 0. So to write the circle equation means x square plus y square equal to some constant square. Now to write like that, we just add, see here, both sides we are going to add 1 by r plus 1 whole square, right? So consider this is the complete equation. To this equation, we are going to add both sides 1 by r plus 1 whole square. Okay. Now in order to add that one, see, u square minus 2 into r by r plus 1 plus into u plus v square. Okay. Plus, and see, r minus 1 by, consider this equation, and by adding 1 by r plus 1 to that respective equation, we'll be having here, see, u square plus v square minus 2 into r by r plus 1 into u. Then here r minus 1 by r plus 1 as first term, plus we are adding 1 by r plus 1 whole square on both sides, then equal to. See, if you consider both sides, see, if you gets cancelled, 1 by r plus 1 whole square gets cancelled on both sides, then the complete equation remains the previous one only. It won't change. So now to write the circle equation here, see, u square minus 2 into r by r plus 1 into u plus v square. Okay. Plus, see, r minus 1 by r plus 1 plus 1 by r plus 1 whole square. See, r minus 1 by r plus 1 plus 1 by r plus 1 whole square. Between these two, we are going to write, see, LCM is here r plus 1 whole square. Now already r plus 1 is there, r plus 1 into r minus 1 plus 1, right? Which is equal to a plus b into a minus b, a square minus 1. That becomes r square minus 1 plus 1 by r plus 1 whole square. Okay. So plus 1 minus 1 gets cancelled. R square by r plus 1 whole square, or collectively we can write it as r by r plus 1 whole square. Okay. So now from this we'll be writing here r square by r plus 1 whole square, or r by r plus 1 whole square, which is equal to 1 by r plus 1 whole square, right? So u square minus 2r into r by r plus 1 into u plus v square plus r square by r plus 1 whole square, which is equal to 1 by r plus 1 whole square, right? Now u square plus this term means, if you take this r by r plus 1 whole square as here, u square plus r square by r plus 1 whole square minus 2 into r by r plus 1 into u plus v square equal to, on RHS we have 1 by r plus 1 whole square. 1 by r plus 1 whole square. See here, u square, this is a square, and b is r by r plus 1 whole square as b square, and minus 2a value as u, and b as r by r plus 1. 2a, b. So a square plus b square minus 2ab formula is given by a minus b whole square, right? What is that value here? A minus b, r by r plus 1 whole square, right? So from all these three, we will write vu minus r by r plus 1 whole square plus, and v square only left out. Now from this v square, we will be writing it as v minus 0 whole square, which is equal to 1 by r plus 1 whole square, right? See here, x minus a whole square plus y minus b whole square is equal to some radius square, right? So this is the equation for circle, that is u minus r by r plus 1 whole square plus v minus 0 whole square equal to 1 by r plus 1 whole square, right? So now from this equation, see here, u minus r by r plus 1 whole square plus v minus 0 whole square is equal to 1 by r plus 1 whole square. Right? So for a constant value of r, the above equation represents a circle in gamma. Gamma means reflection coefficient plane as the value of x varies with the center. Center means what is that value? A comma b. In place of a here r by r plus 1, and in place of b what we have? 0. Right? So this is representing center, and the radius is given by 1 by r plus 1. See, for a constant value of r, the above equation represents a circle in the reflection coefficient plane as the value of x varies with the center, that is r by r plus 1, comma 0, and the radius 1 by r plus 1. Right? So this is the equation is called constant resistance circle equation. Right? So this looks like ax minus a whole square plus y minus b whole square is equal to r square. Right? So here a and b are resembles the circle center, and those are the values given by r plus 1 comma 0, and the radius is 1 by r plus 1. Right? So this is the equation called constant resistance circle. Right? Now to write the constant reactance circles, so to get the constant resistance circles, what we have considered real part of the normalized impedance equation. Now to get the constant reactance circles, we need to consider reactance part of the normalized impedance. Right? So that is given by here x is equal to 2b by 1 minus u whole square plus b square. Right? So now consider the reactance part. Now to get the reactance circles, see, consider x is equal to 2v by 1 minus u whole square plus v square. Okay. Now from this, if you now consider this as in the cross multiplication between these two. Now from this, we are going to write 1 minus u whole square plus v square, which is equal to, take this as x into denominator, then it becomes 2v by x. See, 1 minus u whole square plus v square equal to 2v by x. Now from this, see, expand this 1 minus u whole square as the a minus b whole square form, then it becomes a square value as 1, b square as b, that is u square, minus 2ab as 2u plus v square equal to 2v by x. So here also now to write the circle form, we are going to add on both sides, or from one side only 1 by x square. Right? See, minus 1 by x square plus 1 by x square. See, in the previous equation, these four are existing. 1 plus u square minus 2u plus v square minus 2v by x is equal to 0 is there in the previous equation. To write the circle form, we will be adding here 1 by x square. Right? So this, see here, minus 1 by x square plus 1 by x square. If these two gets cancelled, the equation remains the previous statement only. Right? Now 1 plus u square minus 2u plus v square, and take this 2v by x into here, v square minus 2v by x plus 1 by x square, and take this minus 1 by x square at the last, equal to 0. See here, a square plus b square minus 2ab. Now from this, we are going to write a minus b whole square, and a value is to be considered as here u. U minus 1 whole square plus v square minus 2 into v by x means 2b, a value as b and b value as x, 1 by x. Right? So v square minus 2 into 1 by x into v plus 1 by x whole square. A square minus 2ab plus b square, which is equal to a minus b whole square, nothing but b minus 1 by x whole square. Now from this, u minus 1 whole square plus v minus 1 by x whole square equal to, and take this 1 by x square into RHS, then it becomes plus 1 by x square. As usual, it looks like circle equation represents x minus a whole square plus y minus b whole square equal to radius square as r square. Now from this equation, what is the value of a and b? A is 1 and b is 1 by x. This is given as center for this reactance circles. And in place of r, what we have here, 1 by x means radius is given by 1 by x. Right? See, for constant value of x, the above equation represents a circle in complex reflection coefficient plane as the value of r varies, with the center as, what is that center? 1 comma 1 by x, and the radius is given by 1 by x. Right? So this is the equation called constant reactance circuits. Right? So from this constant resistance circles and reactance circles, we are going to substitute different values of R in the resistance circles and different values of X in the reactance circles. Now from this, we will be drawing Smith chart. From the Smith chart, we are going to calculate reflection coefficient of a transmission line and the standing wave ratios of a transmission line. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.